Now, so far, we predicted the phase coexistence lines and in the phase diagrams using experimental data of the systems we wanted to study. Another way of predicting a phase diagram is to use an equation of state. And we've already used one equation of state, which is the ideal gas equation of state, stating that pressure times volume equals number of particles times Boltzmann constant times temperature, dividing by volume and non-dimensionalizing it, like using, for example, Lennard-Jones. We can write that as pressure equals density times temperature. And we can expand this because the ideal gas equation only works for very dilute gases. But we'd like an equation of state that can go to higher densities, and then the equation of state can be expanded. So if we divide pressure by rho T, then the ideal equation of state has 1, and we can expand it in powers of the density. Now, here's an example of that. So here I've done some simulations on Lennard-Jones atoms at very low densities, say up to then a reduced density of 10 to the minus 2. There's only a few percent errors, and then as you go above that, the errors start to get larger, and going to higher densities, clearly the ideal gas equation of state is extremely far off the mark. And here I've also plotted a third order virial expansion that fits nicely, at least up to some point. Now, if we want to get closer to a real equation of state than that, then we'll have to go one more step. And that is to say, well, there is a smallest possible volume. As we're compressing these molecules closer and closer, they cannot get closer than a certain distance. And this means that there is a smallest possible volume. So the volume that we need to use in the equation of state, in this ideal equation of state, is not the real volume, but we have to subtract a smallest possible volume, and where this B parameter is the molecular diameter to the third power. So which is 2 times sigma 3 if we use the Lennard-Jones parameters. This can also be expressed in terms of the critical volume of a substance, and so this B parameter is the critical volume divided by 3 times the number of molecules. So going one, but still, the virial equation and the Clausius equation and the ideal gas equation, they only consider repulsive interactions between the molecules, which means that they can never really have a condensation behavior. They can never really condensate from a gaseous state to a liquid state. There is no way of really getting a phase transition with these models. So in order to get a phase transition, we, in addition to adding this excluded volume at high densities, we have to subtract a short-range attractive force. And this parameter is, the first part is a potential energy of one molecule, which is proportional to the number of particles divided by the volume. So it's proportional to the density. So it's some parameter times the density, because and the potential energy of all molecules we have to multiply by the number of molecules, and the pressure that is related to the potential energy with an attractive potential is the derivative of the potential energy. So we take the derivative then, so that means divide by volume once more. So that's how we get this form of the pressure, and since it's an attractive energy, this should be a minus h, it has to be subtracted from the pressure. Now this A parameter, it can be related to the critical pressure and the critical volume, or it can be related to the volume of a particle. So this is the volume of a single particle. And so here I'm just comparing the different equations of state that I've shown so far to a simulation of Lennard-Jones changing pressure and temperature. And we see that the van der Waals equation of state follows it quite closely. Ideal gas, of course, does deviate. The Clausius, it gives a too high pressure, at least at these conditions where I've shown here. But as I said, the main thing that makes the van der Waals equations of state interesting is that it can get a phase transition. It's not. So I'll show this graphically, and we'll have some exercise later doing this numerically, and I'll show this in a plot where we're using the reduced parameters, and we're using the principle of corresponding state, using the critical point as the reference point for the principle of corresponding states. So this means that we are using reduced parameters of temperature, which is temperature divided by critical temperature, pressure divided by critical pressure, and volume divided by critical volume. And then the van der Waals equation of state can be reformulated like this, where it's like this. And if we plot isotherms at so these are curves of this van der Waals equation of state at different temperatures. So here you see has temperature 1.1 it's all the time it's got a monotonous slope. At the critical temperature, so at reduced temperature equal 1, it has a point where the slope is 0, and going to temperature lower than the critical temperature, we see that we get inversions of slope. So we get we get a negative, well, not only a negative slope but a positive slope, and which means that this is in some sense completely unphysical. We know that below the critical point, the black line here is the phase coexistence line, and we can calculate this, which you will do in a later exercise. We can calculate this coexistence line by requiring that the area connecting the liquids, the gas side and the liquid side of the phase diagram has the same area above, between this straight line and the isotherm, and as the area here between the straight line and the isotherm. There is one more curve that I'd like to mention, which is the inflection point of the curve. So this is where the in fact where the double derivative of the Gibbs free energy is 0. So it's the inflection of point of the isotherm, and this corresponds to a is called a spinode, and inside of the spinode here, the mixture of liquid and gas is completely unstable. Between the outer curve, the saturation curve, and the spinodal, it is metastable in these regions. So I will not do any formal derivation of this Maxwell construction now. This will leave for some exercises. But we will use the van der Waals equation because it is the simplest equation of state that gives us a phase transition. It gives a critical point and all the main behavior of a liquid gas system.